Hello everyone. Today we are going to see why the complex numbers are used in AC circuit analysis. Before understanding why complex numbers are used in AC circuit analysis, we have to understand what is RMS value. To understand this, I am going to consider this picture. So in this, I have taken this sinusoidal waveform which is having a peak value of 110 volts. Similarly, it has a frequency of 50 Hz and I want the RMS value of this sinusoidal voltage source. So it has, I am going to call this as a V of t. Now, what is the RMS value? As the name itself indicates, RMS means it is root V square value. So first, I am going to square this waveform. I have this waveform. I will square this waveform. When I square this waveform, I am going to get this waveform. Okay. You can see, for example, here I have a value of 110. Okay, so 110 into 110. So this is having a very high value, which is around 12k. In the similar way, here it is 0 into 0. I am going to get the 0 value. In this way, at every instant, the value is being squared and I got this waveform. Okay, so I got the squared waveform. Now I need to take the mean of this squared waveform. Okay, so I have to take the mean of this squared waveform. Mean is nothing but the area under this curve divided by base value. So to get this area, I am going to square this waveform. Sorry, I am going to integrate this waveform from 0 to t. Okay, so this entire thing, that is v square of t into dt under the integration of 0 to t, gives me area under this squared curve, that is the red area here. Okay, and I will divide this area by base value. Base value is nothing but t here. When I do this, I am going to get the average of the squared value, squared waveform, or mean of the squared waveform, and I am going to take the root of this entire thing. That becomes the RMS value. Okay, so what you have to understand here is, if this area is larger, our RMS value will be more. Okay, so this is one of the important observation that has to be made to understand why complex numbers are used in AC circuit analysis. Okay, to understand why complex numbers are used in AC circuit analysis, I am going to use a simulation to show how the waveforms are added. I am considering a sinusoidal voltage source. As you can see here, the peak value of this sinusoidal voltage is 110 volts and it is having a frequency of 50 Hz. Similarly, I have another voltage source, the V2, which is having the same value as V1. V peak is equal to 110 and it is of 50 Hz. Okay, now I have connected both of these in series. You can see here. Similarly, to measure the voltage V1, I have connected a voltmeter, that is VP1, which measures the voltage V1. Similarly, the voltmeter VP2 is connected to measure the voltage V2. This is connected to a resistor R of 10. Okay, now now if you see, if you run this simulation, I am going to get the waveform of these two voltage sources. So I will show that waveform. See here, this is the waveform. I have a V1, you can see the V1 here. Similarly, I have a voltage source V2. V2 is plotted, and I have added these two things. Okay, VP1 and VP2 is there. I have added these two things and I will get this VP1 plus VP2 voltage. Now see here, see, note this pointer. So what this pointer indicates is, at 40 millis at uh, I think it is 40 milliseconds or 4 milliseconds, sorry, it is 4 milliseconds. At 4 milliseconds, I am having a VP1 of 104.7. Similarly, VP2 is 104.7 and the VP1 plus VP2 is 209.4 volts. So if you observe this one, these two things are added arithmetically. You can see here, it is 104.7, 104.7. If you add them, you are going to get 20.40. In the same way, at every instant, these two voltage sources are added. Now this is about instantaneous value. Here the instantaneous values are added arithmetically. The same thing we will measure the RMS value. So this RMS value can be seen here. RMS value of voltage sources can be seen. I have this RMS value. See, VP1 is having a RMS value of 83.64 volts. Similarly, VP2 is having a voltage of 83.64 because both of these things are same. Okay, and I have the RMS value of VP1 plus VP2 as 167.29 volts. It is plus 2 here, so it will be 167.29 volts, which is nothing but 83.6 plus 83.6, that is equal to 167.29, which is again a arithmetic addition. We are just adding the two voltage sources. RMS value of this one, RMS value of VP1 plus RMS value of VP2 will be equal to the RMS value of VP1 plus VP2. Now I am going to do the same thing, but I am going to introduce a phase difference. Here both these VP1 and VP2 are in phase. Now I am going to introduce a phase difference and see, I will see what is going to happen for this RMS value. Now let's consider a second diagram. Here I have a voltage source V1 which is having a phase angle of 0 degrees. Similarly, I have another voltage source which is having a phase angle of 30 degrees. The peak value and frequency of these two voltage sources is equal, but they have only phase angle difference. Now I will run this and I will see the waveforms. So you can see here I have the VP1 and I have the VP2. Similarly, I have a VP1 and VP2, and at this instant, that is 4 milliseconds, you can see the value of VP1 is 104.70 volts, but VP2 is 107.53 because it is shifted by an angle of 30 degrees. You can see here it is leading this voltage source, leading VP1 by 30 degrees, so it has a value of 107.53. Similarly, when you add these two things, VP1 plus VP2, which will be equal to 212.24. Again, here the arithmetic addition is being done. The same kind of thing happens for entire waveform. You can consider any instant and you can check that the waveforms will be added arithmetically. Instantaneous value can be added arithmetically. But now we will consider the RMS value. You can just see the RMS value here. VP1 is having a value of 83.64, but VP2 is having a value of 80.75. The sum, that is VP1 plus V2, VP2. The waveform VP1 plus VP2 is having a RMS value of 160. If you add these two things, it should be 163, but I have only 160. The same kind of a thing we are going to do now. I am going to increase the phase angle difference. You can see here I have done the same thing, but I have considered the phase angle of V2 as 90 degrees, and I will run the same thing. You can see I have the waveforms here. The VP2 is shifted by VP1 by an angle of 90 degrees, and you can see here at 4 milliseconds I have VP1 is equal to 104.70. Similarly, VP2 is 33.72. Similarly, I have VP1 plus VP2 which is equal to 138.4. Again, here the arithmetic addition is being done, but if you see here the RMS value of VP1 is 83.64, VP2 is 71.43, but the RMS value of VP1 plus VP2 is 109.97. You can see here it is 83, it is 71, it should be around 150 or 160, but I have only 109.97 volts. So what is the meaning of this? Because we are not having arithmetic addition here. Okay, so arithmetic addition of RMS values cannot be done. Similarly, I will consider another instant. I have one voltage source VP1 which is having a phase of 0. Similarly, another one is having a phase angle of 180 degrees. Now, can you tell me what will be the RMS value of VP1 plus VP2? I will give 5 seconds. 1, 2, 3, 4, 5. Now we will see what is the answer for this one. You can see here I have one waveform VP1 and I have another waveform VP2. Okay, and I have this VP1 plus VP2. You can see it is 2 e raised to power minus 11, which can be ignored, which will be almost it is equal to 0 now, because here I have a positive value, but here I have a negative value. If you add these two things, the value is going to become 0. This thing happens for every instant. So I have the instantaneous value here as a 0, and I will see the RMS value. RMS value of VP1 is 83.64. Similarly, RMS value of VP2 is 83.64. If I add these two things, I am going to get VP1 plus VP2. Sorry, the RMS value of VP1 plus VP2 is 0. You can see it is e raised to power minus 11, which is 0. Okay, so one thing we have to understand here is this is not addition, not arithmetic addition. Okay, and here this phase angle difference is creating a problem for this kind of arithmetic addition. Okay, so now we will see why this thing is happening. If you see the first waveform, if you see this waveform, okay, if you see this waveform, now here what is happening is when the VP1 is positive, when VP1 is positive, the VP2 is also positive. Okay, so when you add these two things, the VP1 plus VP2 becomes added, and I'm going to get a large value here. Okay, similarly the same kind of thing happens in negative side also. Here it is negative. When VP1 is negative, the VP2 is also negative. Okay, and because of which here also this negative are going to add, and I'm going to get a larger negative value. Now when you take the RMS value of this one, when you take the RMS value of this one, as I told you in the first case, this will be squared. Similarly, this will be squared. When you square, this also becomes positive, and I am going to get positive RMS value, which will be the sum of RMS values of these two things. Okay, and the same kind of a thing here. What happens? For better understanding, we will consider this example. So here what happens is when I have this VP1 is positive, some part of this is negative. You can see here. So if you see this portion, VP1 is positive whereas VP2 is negative. Okay, some portion you can see here. VP1 is positive whereas VP2 is negative in this portion. Okay, so when you add these two things, here they get subtracted. Okay, so here VP1 it is minus because it is negative, they get subtracted, and I am going to get this waveform. Okay, so in the similar way, when I have this 180 degrees, the same kind of a thing is going to happen. Here it is positive, here it is negative. When you add them, they become 0. Okay, so here if you observe these things, you will conclude, you will understand one important observation here. This kind of arithmetic addition cannot be done for this RMS value, and it is mainly because of phase angle difference. Okay, so if we do not have any phase angle difference, then there will not be any need for complex numbers. Okay, so when two waveforms are in phase, you can directly add them to get the RMS value. Okay, so the same thing is done in the first case. So here it is the 83.64 plus 83.64, which is equal to 167.29, because these two waveforms are in phase. Okay. Now we will see why complex numbers are used. Now you understood that because of this phase angle difference, the RMS value cannot be added. Okay. So now we will see how this kind of a problem can be overcome. So we concluded one important thing here is that normal arithmetics cannot be applied here. Okay, so I want something different here. You can see here I have this 83, but I have this 80. The sum of these two things should be equal to 160.10. Okay, so here I have this problem, and normal arithmetics cannot solve this problem. Okay, so cannot justify this answers. Okay, so here it is 83.64, here it is 80. The sum of these two is 160.10. Okay, so this can be justified using the complex numbers that we will see. Okay, now let's consider this diagram. Here I have one body and a person is pulling it with the force of 20 Newton in this direction. In the similar way, another person is also pulling the same body with the force of 20 Newton. What will be the total force applied on this body? You can just see here, it will be equal to 40 Newton, because both these things are adding to each other. The same kind of a thing can be seen here. So a person is pulling the body with the 20 Newton in this direction. Similarly, another person is pulling it with the 20 Newton in this direction. So the resultant is 0 here, because both these things get cancelled. But when I have this kind of situation, when a person is pulling it with the 20 Newton and another person is pulling it with the 20 Newton, same force, but he is applying this force at an angle of 30 degrees with respect to the first person. So here, what will be the resultant? If you see this kind of a thing, the resultant force will be the vectorical sum of these two forces. Okay, this situation is similar to that now we just now discussed about sinusoidal waveforms. Okay, so I have two waveforms. When they are in phase, I am going to get this kind of a thing. They get directly added and I am going to get a 40 Newton. Similarly, when they are at 180 degree displaced, both these things get cancelled and I am going to get a 0 Newton. Sorry, 0 RMS value. The same kind of a thing when it is shifted by 30 degrees, you were seeing that it was not equal to the sum, but it was lesser than the sum. Okay, so what I can conclude here is the problem of this RMS value can be solved if we assume this sinusoidal waveform to be a vector of this kind. Okay, so when this sinusoidal waveform is represented as a vector, and if you do the vector addition, then this kind of a problem can be solved. And as you all know that a vector is represented by a complex number. When I have this kind of a vector, this is represented as a 20 Newton at an angle of 0. Okay, similarly this is represented as a 20 at an angle of 30 degrees. Okay, in the similar way, the sinusoidal waveforms are also represented by vectors. Okay, but what is the difference here is these vectors are going to rotate because it is sinusoidal in nature. Okay, so it should be continuously moving. To represent that, they consider that these two things will be rotating with the angular velocity. Okay, omega. So this rotating vector, they called it as a phasor, and they called it as a phasor, this rotating vector. Okay, and when we apply this kind of a thing, the same thing is done for sinusoidal quantities. The RMS value, for example, in our case, the RMS value was 83. If you observe that this value, this sinusoidal quantity which was having a 0 phase angle, was represented in this direction with 83 as a RMS value, and it is represented as 0. Similarly, the other vector, if you see the second waveform, that is image second, there I had a 30 degree angle of difference. Okay, so there it is, there it will be represented as a 30 degrees at an angle of, sorry, 83 volts at an angle of 30 degrees, and both of these two things will be added vectorically, so that I am going to get the resultant RMS. Okay, so what I want to say here is this kind of observation that is made for sinusoidal voltages can be solved by applying these kinds of vectors, vector algebra. Okay, so because of which the vector analysis is put in AC quantities. Okay, I hope you understood what is the necessity of using complex number in sinusoidal analysis. Now we will consider its practical applications. So to understand that, I have considered this circuit diagram. Now I will run it and I will show the wave. See, this is the waveform results. You can see the VR1, the RMS value of VR1 is 86, sorry 8.6. Similarly, the RMS value of VR2 is 86. If I add these two things, it will be 95. Here direct arithmetic addition is being done because they are in base. Okay, so when there are resistors connected in series, only resistors are connected, you can directly add the voltage across each resistor to get the total voltage. Similarly, I will consider now a resistor and inductor combination. Okay, I will run this and I will see the waveform. See, to better understand, I have considered the ammeter here, okay, to measure the current. You know that this is the circuit current, and you know that there is a resistor in the circuit, then the voltage across that resistor is VR1, and this VR1 and current I1 are in phase because it is a resistive circuit. Similarly, I have VR2, which is the voltage across inductor, and the voltage across inductor leads the current flowing by an angle of 90 degrees. Okay, the same kind of thing is happening here, you can see, and the same thing can be verified in other part of the waveform. Now we'll come to the RMS value. See here, the RMS value of VR1 is 75, whereas the RMS value of VR2 is only 22.83. Now if we add these two things, it will be around 95 volts, but the applied voltage is only 78.34. So is this the violation of KVL? Because the supplied or the RMS value of the applied voltage is only 78, but the sum of the voltage across resistor and inductor is 95. So here this KVL is still being verified, but this addition or the addition of VR1 and VR2 has to be done using vector algebra, not arithmetic algebra. Okay, so this has to be done using vector addition. Then you are going to get it as a 78.34. So you have that parallelogram addition for this one, that is 75.5 whole square plus 20 22.88 whole square plus 2 into 75.5 into 22.83 cos of the angle between this VR1 and VR2 under square root. If you do that, you are going to get this as a 78.34. So I hope the concept is clear. You have to just see the first waveform where I explained about the RMS value, and you have to compare that diagram with other waveforms and see what is the necessity of using complex numbers for this kind of a sinusoidal analysis. If you have any doubts about this topic, you can put it in a comment section. Also, if you want me to, if you want any videos related to electrical, kindly mention its topic in the comment box. And if you like this video, please press the like button and also subscribe to my channel, or and you can share it as much as possible. Okay, so thank you.